Hello everyone. In this lesson, we're going to be introducing another one of vector operations known as the cross product or the vector product. And because the result of this operation is going to be a vector, we're going to look at both the magnitude of this vector and the direction of it. First, looking at the magnitude, we can use the definition of the following definition. So this is the magnitude of the cross product defined as the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between the two vectors. So in this diagram, we have vector A and we have vector B, and we have an angle between them that's called theta. And as you see here, I've dropped a perpendicular line from the end of A onto B, so I get a right triangle. And I'm going to go ahead and label the size of this triangle as aparallel and aperpendicular. So aparallel, which is the one we use in dot product, which I cover in another video. So I'm not going to talk about that here. So the parallel component is going to be a cosine theta, and we use that in the definition of dot product. But the aperpendicular component, this is the component of A that's perpendicular to B. That is what we use in cross product. So magnitude of A times sine theta can represent the perpendicular side of that triangle. Now, how do we find the direction? One way we can find the direction of a cross product is using something called the right-hand rule. So for this, we actually can use our right hand. So this is actually my hand. So the way we perform the cross product and find the direction with the right hand rule is we always start a stretched palm along the direction of the first vector. So if I'm going to do A cross B, my stretched palm has to be in the direction of A. And then I have to close my basically fist in the direction of B, the second vector, and then my thumb will denote the direction of C, which is the resultant vector. So what I'm showing you is the first step on the left is to stretch your palm in the direction of the first vector, then close your fist towards the second vector. So the orientation of the hand has to be such that when you close your fist, it's going to be in the direction of B. And in that situation, C, or the thumb, is going to be in the direction of the resultant vector. Now, just like, so one of the examples of the use of cross product in physics is in the definition of torque. So torque is what causes an object to rotate. So just like force causes an object center of gravity to move in a space, so we call that translation in physics, torque is what causes an object to rotate about an axis of rotation. So in this question, we have the figure, a disk basically here, and there is a force at an angle. So here the question says, in the figure below, a 30 Newton force is applied at an angle of 30 degrees with respect to the radial direction. So radial direction is in the direction of radius. So when you draw the radius, radial direction by definition is in that direction, actually away from radius, causing a solid disk of radius 5 meters to rotate about its center. So the radius of the disk is given as 5 meters here. It says calculate the torque exerted on the disk by this applied force. So first we look at the definition of torque, which is R cross F. R is known as the lever arm or the moment arm. And it is in fact a vector. It starts from the origin, drawn in yellow. It starts from the origin, which is called the pivot point. This is where the axis of rotation is. And it ends at the force's line of action, or basically where the force is. And what we do, we first place the force and the moment arm vector in one together at the same origin. So this is what I do right here. I place the two vectors that I want to take the cross product at the same origin. And then I go ahead and calculate the magnitude using the definition. So the definition of magnitude was take the magnitude of the first vector, in this case force, times the magnitude of the second vector, in this case going to be the radius or moment arm or the lever arm vector, and then times the sine of the angle between the two vectors. So R is 5 meters, the force is 30 newtons, and sine of 30 degrees, which is 1/2, the product of all that is going to give us 150 over 2, which is 75 Newton meter. And in this case, we're not going to call this joule like we do in work. This is actually kept as Newton meter. That is the unit of torque. So very practical application of cross product, showing up first time in mechanics in the context of the definition of torque. And here's an example where we applied this definition to find the torque in this problem. The next piece of the puzzle is how do we deal with cross product in what we know as the component form, as a vector equation, or in the component form. So here I'm given vector A in the component form, in the vector equation form, as ax I hat plus ay j hat plus az k hat. Similarly, with vector B is given as bx I hat plus by j hat plus bz k hat. By the way, I hat, j hat, k hat are the unit vectors along the positive x, positive y, and positive z direction, respectively. They're called unit vectors because their magnitude equals to 1. So these are called unit vectors for the reason that their magnitude by definition is 1, and therefore if a vector's magnitude is 1, all that's left is the direction of that vector. So these three unit vectors point to the cardinal directions along x, y, z axes. To do this, we're going to use the determinant of the following matrix. So what we're going to go ahead and do, we're going to use the determinant sign. So A cross B equals to the determinant of a 3x3 matrix. And we're going to go ahead and place the unit vectors on the top row. So the way we do cross product with this determinant is by placing the unit vectors on the top row, I hat, j hat, k hat. Then we place in the next row, we place the components of A, the first vector, so ax, ay, az, and then we'll place in the third row the component of the second vector, bx, by, bz. So that's the first step of the process. The next step of the process is to assign positive and negative signs to that top row. So it's starting with positive sign and alternating. So it goes as I hat taking a positive sign, j hat taking a negative sign, and k hat taking a positive sign. And all we do for a second is just writing these signs on top of I hat, j hat, k hat. Next step in the process is starting with the I hat, we go ahead and cover that row and that column where I hat is. So I'm going to show you right here. So where I hat is, the first thing I do actually, I write down I hat here, positive I hat. Then I open parentheses and then I do this. I cover the row and the column, and what I get is this 2x2 matrix. And then I have to do the determinant of this 2x2 matrix in the parentheses, which is the product of the main diagonal, AY, BZ, minus the product of the minor diagonal, AZ, BY. So that is going to take care of the first term. For the second term, we do the same thing. We go use the negative j hat. So we write down negative j hat right here. Open parentheses, then we cover the row and the column where j hat vector is, and we end up with, again, a 2x2 matrix, ax, bz, and we do the determinant of that, ax, bz minus, say it, az, bx. Very good. So that takes care of our second term. And then we go to the last term, the k hat term. For the k hat term, again, the same thing. We do plus k hat. First, we write that, plus k hat. Then we go ahead, open parentheses, cover that row and that column, and then do the determinant of the 2x2 matrix. Ax by minus ay bx. And that is how we can take care of the cross product in all of its glory. In fact, this will be a vector equation. What we get as a result of this in component form is another vector in component form, and that basically it has in it the information for magnitude and direction. So let's take a quick look at a quick example of this. So here's vector A in component form, and this time I wrote it in component form. 2 comma 3 comma 0, that means 2i hat plus 3j hat plus 0k hat, and B is going to have components of -1 comma 5 comma -2, and we just repeat that process that I just showed you earlier with these numbers, so that we're going to end up getting a number as a result of this. So here we again replaced in the first row, we placed the unit vectors as we did earlier. Then the second row, we're going to place the component of the first vector A. And in the third row, we're going to place the component of the third vector B. Second vector B. So component of the unit vectors, first row, components of the first vector, second row, component of the second vector, third row. All right. And we repeat the process. So we go plus I hat, covering the row and the column. I've done that in yellow here for you guys. So once we get that 2 by 2 matrix, we get 3, -2. When we cover I hat, column and row, we get 3 times -2 minus 0 times 5. Then we go to -j hat. Covering that row and column, we get 2 times -2 minus 0 times -1. Plus k hat, covering that row and column, we get 2 times 5 minus 3 times -1. That's it. Then we just go ahead and do the little arithmetic there. 3 times -2, that's -6. 5 times 0, that's 0. So we get -6 minus 0 for the first component, which is -6. So we can eventually write it as -6 I hat. And with the second component, we got 2 times -2, that is -4. Then minus -1 times 0, that's 0. -4 minus 0, that's just -4. But this is a negative j hat, so that negative times negative becomes positive. That becomes positive j hat, positive 4j hat. And then for the k hat component plus k hat, we got 2 times 5, 10. 3 times -1, -3. 10 minus -3, that's positive 13. And that is going to be our third component. I hope you guys enjoyed this lesson. Please go ahead and like this video and subscribe to the channel. I'll be updating the channel with more videos to come on the topics of math, physics, chemistry, and computer science. See you next time.